To the nation with the mightiest rocket power belongs the conquest of space.
In January 2013, a young propulsion engineer named Kate Estes walked into a laboratory at NASA's Marshall Space Flight Center in Huntsville, Alabama, and began taking apart a machine that had not been touched in over 40 years. The machine was an F-1 rocket engine, and it had been sitting in the Smithsonian since the 1970s. When Estes and her team pulled it apart piece by piece and compared what they found against the original Rocketdyne blueprints, they discovered something that should have been impossible. The blueprints were almost useless. The drawings were accurate. The dimensions matched. But the blueprints described what to build without explaining how to build it. And the gap between those two things turned out to be pretty big. The engine Estes was disassembling once belonged to the Saturn V, the most powerful rocket ever flown. Between 1967 and 1973, that rocket launched 13 times, carried 24 astronauts toward the moon, and never once failed. 5 F-1 engines powered its first stage, producing a combined 7.6 million pounds of thrust at liftoff. The 5 of them together consumed more fuel in the first 2.5 minutes of flight than a commercial jetliner burns crossing the Atlantic, and nobody in 2013 fully understood how they were made. The F-1 started as a weapon. In 1955, the United States Air Force asked Rocketdyne, a division of North American Aviation in Canoga Park, California, to study whether a rocket engine could produce 1 million pounds of thrust. Then the Air Force lost interest because no missile needed that much power. The engine sat on a shelf until NASA came along in 1958, took one look at it, and realized this was the machine that could carry human beings to the moon. There was one problem that nearly killed the entire program. When the F-1 ran at full power, pressure waves inside the combustion chamber would bounce back and forth, building on each other until the engine tore itself apart. Engineers called this combustion instability. And in 1962, it destroyed a prototype during testing at Edwards Air Force Base in a quarter of a second. A 28-year-old engineer named Sonny Morea was given responsibility for solving it. His team tried over 100 different injector designs across more than 2,000 full-scale test firings. The instability was random. Some engines ran perfectly for minutes. Others exploded before reaching full thrust. There was no computer in 1962 that could model the behavior of two liquids mixing and igniting at those pressures, and there was no theoretical framework to predict when the oscillations would begin. So Morea's team did something that sounds insane when you say it out loud. They placed small explosive charges inside the combustion chamber and detonated them while the engine was running. They added copper dividers called baffles to the injector plate, creating compartments that disrupted the pressure waves. For 3 years, from 1962 through 1965, they kept bombing their own engine until the oscillations would die out within 1/10 of a second. That was how the F-1 was made stable. Not through computation, not through simulation. Through repeated, violent, hands-on experimentation that left the engineers with physical intuition for a process nobody could describe mathematically. If you're enjoying this video, subscribing helps the channel grow and lets us keep making these deep dives. On April 16, 1965, 5 F-1 engines were mounted together on a test stand at Huntsville and fired at the same time. When all 5 ignited simultaneously at the Stennis Space Center in Mississippi during later testing, the low-frequency roar shattered the plate glass windows of a bank in Picayune, 15 miles away. The Saturn V was ready, and over the next 8 years, 65 F-1 engines would fly on 13 rockets without a single combustion. But the knowledge that made those engines work lived almost entirely inside the people who built them. December 14, 1972. Commander Gene Cernan climbed back into the lunar module on the surface of the moon, and the hatch closed behind him. At the time, nobody knew that would be the last time. NASA had 3 more Apollo missions planned. The crews had been tentatively assigned. Apollo 18 would have landed at Copernicus crater. Apollo 19 was targeting Hadley Ryle. Apollo 20 had several candidate sites, including Tycho, one of the most scientifically valuable locations on the entire lunar surface. Apollo 20 was canceled on January 4, 1970, less than 6 months after the first moon landing. Its Saturn V was reassigned to launch Skylab, the orbital workshop that NASA hoped would justify its existence after the moon race was won. Apollo 18 and 19 were canceled later that same year. One of Richard Nixon's top aides had told NASA directly that the president did not see the need to go to the moon 6 more times. The agency's budget was cut 15% in a single year. Administrator Thomas Paine wrote to Nixon that the cancellation decision was reached reluctantly, but with overwhelming consensus. The most compelling reason, he said, was the austere funding situation. By 1973, the last Saturn V had flown. The production line was shut down. Boeing, which built the first stage at the Michoud Assembly Facility in New Orleans, stopped manufacturing. North American Rockwell, which built the second stage, moved its workforce to other contracts. IBM, which built the instrument unit that served as the rocket's brain, stopped producing the specialized components entirely. The workforce dispersed. More than 400,000 people had contributed to the Apollo program at its peak, spread across 20,000 companies and universities. Engineers who solved combustion instability went into private industry or retired. The technicians who knew exactly how much pressure to apply when fitting the turbopump housing by hand carried that knowledge home with them and never wrote it down. Rocketdyne, to its credit, saw what was happening. The company launched the F1 Production Knowledge Retention Program, which produced 20 volumes of documentation covering the injector ring set, the valve assemblies, the thermal insulation, the electrical cables, and the checkout procedures. But the program could not capture what the engineers did with their hands. The F1 was largely handcrafted. Complex welds that took a full day to complete were performed by technicians whose adjustments were never formally recorded. Each engine was slightly different, with its own quirks and imperfections that the builders compensated for through experience. The volumes described the engine. They could not describe the act of building it. Over the following decades, the Saturn V's blueprints were preserved on microfilm at the Marshall Space Flight Center. 82 cubic meters of Saturn documentation sat in the Federal Archives facility in East Point, Georgia. But paper without the people who understand it is just geometry. It tells you the shape of a thing without telling you how to make the shape become real. In 2012, something unusual happened. A team of engineers at Marshall Space Flight Center pulled an F1 engine out of storage and another from the Smithsonian's National Air and Space Museum. It had been removed from Apollo 11 before launch due to a glitch and replaced with a different unit, then donated to the Smithsonian in 1970. For 42 years, it had been sitting behind glass, while the knowledge required to run it evaporated from the world around it. Kate Estes and her team were part of a broader effort to see whether F1 technology could inform NASA's new space launch system. They used selective laser melting, a digital manufacturing technique, to produce metal parts the original way required handwork to create. They used 3D scanning to generate computer models from the physical hardware. Because the original blueprints lacked the detail needed to reproduce the components, they ran 11 test firings of the gas generator, the component that powers the turbopump, recording data with modern instruments that did not exist in the 1960s. What they found confirmed what everyone had feared. The pathways from blueprint to finished part were full of undocumented decisions and hand adjustments that only made sense if you already knew why they were there. And the original builders who could have explained had solved problems by feel, scribbled the results on scraps of paper, and moved on to the next engine. Meanwhile, 3 miles below the surface of the Atlantic Ocean, a different kind of archaeology was underway. Jeff Bezos, who had watched the Apollo 11 launch on television at the age of 5, spent 15 minutes on the internet one evening and found the radar-tracked coordinates where the Saturn V's first stage had impacted the water after separation. In March 2013, he sent a team aboard the research vessel Seabed Worker to recover what they could find. The remotely operated vehicles worked at a depth of more than 14,000 feet, tethered by fiber optics and powered by cables, transmitting over 4,000 volts. What they found on the ocean floor looked like a sculpture garden of wreckage, twisted and corroded by 43 years of salt water. They brought back thrust chambers, gas generators, injectors, turbines, and fuel manifolds. They recovered enough hardware to reconstruct displays of 2 complete F1 engines. Most of the serial numbers had been destroyed by the impact and the corrosion. But a conservator at the Kansas Cosmosphere, scanning the hardware under black light with a special lens filter, found a number stenciled in faded paint on one of the thrust chambers. It read 2044, which was Rocketdyne's serial number for NASA Unit 6044. That was the center engine of Apollo 11, the engine that helped carry Armstrong, Aldrin, and Collins off the pad on July 16, 1969. They pulled it from the bottom of the ocean because it was dissolving. Bezos said that the salt water was slowly consuming the metal, and if nobody went to get it, eventually there would be nothing left. Today, 3 complete Saturn V rockets survive. One lies on its side at the Johnson Space Center in Houston. One is displayed at the Kennedy Space Center in Florida. The third, a dynamic test vehicle that was never meant to fly, rests in the Davidson Center for Space Exploration in Huntsville, Alabama. Visitors walk beneath them and photograph the F1 engine bells, which are large enough to stand inside. NASA currently spends roughly $4 billion per launch to send the Space Launch System into orbit. The SLS generates more thrust than the Saturn V, uses engines derived from the Space Shuttle, and took over a decade to develop. It could not have been built without studying Saturn V hardware. But the MILS is not a descendant of the Saturn V in any meaningful engineering sense. It is a new machine, designed from scratch, because the old machine could not be recreated. The manufacturing pipeline, the testing infrastructure, the quality control procedures, the workforce that knew how to beat a turbopump housing into alignment with a rubber mallet, all of it is gone. The Saturn V is often called the greatest engineering achievement in human history. That title is usually meant as a compliment, but it contains something uncomfortable when you look at it long enough. We built the most powerful rocket ever flown, used it 13 times, and then let the knowledge required to build it drain out of the species like water through open fingers. Not because anyone decided to destroy it, not because it was classified or hidden. The knowledge vanished through neglect, through retirement, through the ordinary passage of time in a civilization that assumed anything that important would somehow preserve itself. It didn't. The F1 engine was made stable by engineers who detonated bombs inside their own machine until they understood its behavior through instinct. That instinct retired with them. It could not be uploaded or archived or preserved on microfilm. And when a new generation of engineers came looking for it decades later, they found the drawings and the dimensions and the material specifications. They found everything except the knowledge. We treat our greatest achievements as if they are permanent. We assume that because we did something once, we could do it again whenever we choose. The Saturn V is proof that this assumption is wrong. Capability is not a thing you build and keep. It is a thing you practice, or it disappears. Somewhere in the Atlantic, 3 miles down, pieces of the engines that carried us to the moon are still settling into the sediment, corroding one molecule at a time. Nobody is going back for them, and the knowledge of how to build new ones is already gone.